In this module, we're going to talk about what's called lattice energy and something called the Born-Haber cycle, and we're going to use it to calculate this lattice energy. So first of all, let's look at an ionic compound, sodium chloride, to take an easy one. Now, the energy involved in removing an electron from a sodium atom is its first ionization energy, and that number is positive 496 kilojoules per mole. The energy required, or given off rather, when you add an electron to a chlorine atom is its electron affinity, and that's negative 349 kilojoules per mole. So if you add these guys up, you get a positive number, 147 kilojoules per mole. Now, if that's all that was going on when we made sodium chloride, then it would not happen spontaneously most likely, and it certainly wouldn't be given off in energy. Now, we know, we can do, it's a common demonstration really. When you just put sodium and chlorine together, they react violently, and it's really spectacular, and it definitely releases a lot of energy. So something else has to be going on. Well, that other thing is called lattice energy. Here's the definition. Lattice energy is the change in energy when you take a gaseous cation and a gaseous anion, bring them together, and let them form the solid ionic compound. So this process here, gaseous sodium ion plus gaseous chloride ion coming together to make solid sodium chloride, the change in energy for this process is called the lattice energy. And it ends up for sodium chloride, that number is a negative 788 kilojoules per mole. And all this really is, it's Coulomb's law, but it's a pretty complicated form of Coulomb's law, because when you bring sodium and chloride together, they certainly release energy, but there's all these interactions that go on between not only this sodium atom ion and this chloride ion when they come together, but also with the neighboring ones. So we have, that represents sodium, and that represents chloride. Then when they make a solid, there's going to be a chloride here, here, and here, something like that, right? And then there's going to be more sodiums out here, here maybe. So you kind of get the picture, right? It builds this lattice. Well, if we look at this sodium ion here, it's going to not only be attracted by this chloride ion through Coulomb's law, but also this one, and this one. And remember, this is the real thing, 3D, right? So there's something on top and beneath this, and they're going to interact. And this sodium ion and this sodium ion are going to repel each other, so is this one and this one. This chloride and this chloride will repel each other, and so on and so forth. So it's pretty complicated. The net result of all that is the lattice energy. The Born-Haber cycle is a process. It's imaginary, but it's a process that we can use to calculate the lattice energy, or any of the other processes that occur in this cycle. So here are the steps in the Born-Haber cycle. I know it looks complicated, there's a lot of stuff up here, but just follow one by one. It's really pretty simple, and it's always the same series of steps. So once you get it down, it's just boom, boom, boom. Plug it in, and you got it. So the first step is always to start with the solid ionic compound and break it apart into its component elements in their standard states. Now, sodium in its standard state is a solid, and chlorine in its standard state is a gas. And remember Hofbrinkel? Well, chlorine is one of those Hofbrinkel elements. It's a diatomic in its elemental form, and so it makes Cl2. Now, because we only have one chlorine here, you have a 1/2 right here. The change in energy for this process, we're going to be very interested in that. The change in energy is negative the change in energy of formation. What does that mean? Well, you can look up how much energy it takes to make sodium chloride from its elements. The exact opposite of this reaction right here. When you reverse a chemical reaction, the change in energy for the reverse reaction is the same magnitude but opposite sign of the other direction. So if we look up the change in energy of formation of sodium chloride, it's exactly the opposite of this. So it's the energy we want is a negative of the change in energy of formation for sodium chloride, or whatever compound we're looking at. Next step, always step 2, make everything into a gas. In my example here, sodium is a solid. Chlorine's already a gas. We don't have to worry about it. But if this is something that's not a gas, then you also have to make that into a gas. Let's say it was bromine liquid, then we'd have to vaporize the bromine. But here we go. Chlorine's already gas. We're going to sublimate sodium. That's what it's called when you go from a solid to a gas directly as sublimation. And you can look up the change in energy of sublimation for sodium and some other elements. So that's this second change in energy is the energy of sublimation for sodium. Next step, always the third step, make the cation. In this case, the sodium ion has a +1 charge, so all I have to do is remove one electron, right here, from here to here. Everything else stays the same. This process is called the first ionization energy. You guys know that. The first ionization energy for sodium, that's our delta E3. Now, if we were to make say a positive 2 cations, like maybe it was calcium that we were dealing with, then this change in energy here would be the first ionization energy plus the second ionization energy for calcium, and so on. Next step, always the fourth step. The non-metal is going to have a bond in it. And that's what we're dealing here with. We're dealing with simple ionic compounds where that anion is mostly a halide or some non-metal. So we have to break the bond between these two chlorine atoms to make a single chlorine atom. And you can look that up. It's called the bond energy for Cl2. And now because we only have a half a mole here, we're only breaking a half a mole of bonds. The change in energy for this process is 1/2 the bond energy for chlorine. Next step, always step 5, is make the anion. So the anion is going to be chloride. So now that we've made it into a monatomic gaseous atom, we just add an electron to it. Well, this process here, going from a neutral gaseous chlorine atom to the chloride ion in the gaseous state, is called the electron affinity. You guys know that for chlorine. And we can look that up, and that's the change in energy for this process. And finally, we bring the cation that we formed up here and the anion that we formed right here together and allow them to form the solid ionic compound right where we started from. The change in energy for this process is called the lattice energy, in this case for sodium chloride. I like to draw a diagram like this. I must always do this when I'm doing a Born-Haber problem. And I like the diagram because to me it illustrates really clearly that this is a cyclic process and we start at the same place that we end up, which means that the overall change in energy has to be 0. If we start here and we end up with the same stuff in this imaginary process, overall the change in energy is 0. So the steps that I just outlined for you, 1 is the opposite of the energy of formation, 2 would be the sublimation energy in this case, 3 would be first ionization energy for sodium, 4 would be 1/2 the bond energy for chlorine, 5 would be the electron affinity for chlorine, and 6 is the lattice energy for sodium chloride. When you add all these up, they have to be equal to 0. The way we typically use the Born-Haber cycle is to solve for the change in energy for one of these steps. Usually this, but if we know this, we can find a different one. Doesn't matter. The process is always the same. If you have to know all of these changes in energies except one, and then just solve for the one that you don't know. So let's do a problem. Here it is. We want to find the lattice energy for lithium oxide right here, and we're given this information here. We're given the energy of formation of lithium oxide. This is almost always what you're given, or what you can look up. The energy of sublimation for lithium, the first ionization energy for lithium, the first and second electron affinities for oxygen, and the bond energy of the oxygen molecule. All right, so why don't you pause the video and see if you can work this out, and then check it against what we did over here. All right, so here's my cycle for lithium oxide. Starting with lithium oxide, we make it into its elements. Then we sublimate the lithium atoms, molecule, atoms. Then we make the cation. Then we break the bond in oxygen. Then we make the oxide ion. We bring them back together. So in this problem, which is pretty typical, we're asked to find the lattice energy, which is step 6, delta E6. So just rearranging this, it's negative the sum of 1, 2, 3, 4, and 5. So 1, because there's only 1 mole of lithium oxide, okay, it's the change in energy of that process is negative the energy of formation, which was negative, so that makes that a positive number. Step 2, sublimating lithium. Because we sublimated 2 moles of lithium, go back and look at those numbers, see where that 2 came from. We multiply this by 2, and we get that number. Also, because we have 2 moles of lithium, we're forming 2 moles of the lithium cation, so we take 2 moles times the first ionization energy for lithium. Get that. Again, make sure you know where this 2 comes from. That confuses people at first sometimes. And then what we're doing is we're breaking apart the oxygen molecule. Now, because we only have a half mole of oxygen, well, again, look, see where this guy came from, this 1/2. We multiply the bond energy of oxygen by 1/2, and we get this number. And step 5, we form the oxide ion. Now, because this has a -2 charge, we have to add up the first electron affinity and the second electron affinity, which is actually positive. But we only have 1 mole of oxygen, so 1 mole times the sum of these gives us this number right here. Finally, because what we want, the energy for step 6, which is the lattice energy, is negative the sum of these guys. If we add 1, 2, 3, 4, and 5 up, we get 2,810 kilojoules. And the lattice energy is negative of that, so we get negative 2,810 kilojoules for the lattice energy of lithium oxide.